Alright, today we're going to have a look at the square root of complex numbers. Now, an important part of taking the square root of complex numbers is the idea of real and imaginary components of a complex expression. So one of the best go-to strategies in solving equations involving complex numbers is equating real and imaginary components. So for example, if we had the equation a plus ib is equal to I, well, since we're not allowed to add real and imaginary components together and get one thing mushed together, then the real component of this must be equal to 0 because there's no real components on the right hand side. So we can say, in other words, a is equal to 0, and the imaginary component, if we've just got an I, well, the coefficient of I is 1, which meant b is equal to 1. Now we can abbreviate the real and imaginary components of complex numbers through REZ and IMZ. So REZ, I say REZ, is equal to 3 in this one, and IMZ is equal to 4. Importantly, the imaginary component is not 4i, it's just 4. So in this part here, the real component of z is root 3, and the imaginary component of the complex number z is equal to minus 2. Now, of course, it's not the best in this question to say REZ because none of these complex numbers have defined to be z, but you get the idea of what we're doing. This part, the real component of our complex number is 4. The imaginary component is actually 0. There is no imaginary component. And then similarly, the real component here is 0. There's no just constant number plus on the end, whereas the imaginary component is 5. Now we can apply that to solve complex equations that look funny, and it looks like there's too many variables to solve this equation, but it actually is very solvable. These are both imaginary components, which means real. These are both real components, which means that the real components of the left-hand side have to be equal to the real components of the right-hand side. So a plus 2 is equal to 4, and the imaginary component is, well, this is the same as saying I, b minus 3. The imaginary component is b minus 3, and that has to be equal to minus 2. So here we've got b is equal to 1, and a is equal to 2. Okay. Now, we've already determined things earlier, like the square root of minus 4 is 2i. But what if we wanted to know things like the square root of I or the square root of 2 plus 3i? What we're going to do is utilize this formula here in this box. If z is a plus ib, then square root x plus iy will satisfy this equation. X squared minus y squared is the real component of our question, and 2xy is the imaginary component of that question. And in class, I'm going to go through a proof of that. So, for example, let's find the square root of 3 plus 4i. We're going to say that x squared minus y squared is equal to the real component of 3 plus 4i, and 2xy is equal to the imaginary component. And we're going to set up a set of simultaneous equations, so we can say obviously that y is 2 on x. I'm going to substitute that into the above equation. X squared minus 2 on x squared is equal to 3. So if we solve that, if we expand, we've got x to the power of 4 minus 3x squared minus 4 equals 0. Now, it looks a bit tricky to solve that, so we're going to utilize something called a u substitution. So let u equal x squared. And that gives us u squared minus 3u minus 4 equals 0. So u minus 4, u plus 1 equals 0, which means u is 4 or minus 1. But we said earlier that u was x squared, so x squared is 4, or x squared is minus 1. Now you might think, oh, well that means x is plus or minus 2, and that means x could also be plus or minus I. but we're actually going to exclude that solution because x and y actually belong to the real numbers. X and y are the coefficients of our answer, not the imaginary component themselves. So x and y belong to the real numbers. And we use that notation there, belongs to the real numbers, which is just a little r that's called a double stroked r. It has two lines there, so it's a double stroked r. Now if x is plus or minus 2 and y is 2 on x, well that means y is plus or minus 1, 2 divided by 2. So we're going to say our answer is therefore plus or minus 2 plus or minus 1i, which we could just say is plus or minus 2 plus I. Okay. I might do one more example and then I'm going to stop the video. So we can use this idea to solve equations involving complex numbers. And often and in fact for this one we're going to use the quadratic formula. So using the quadratic formula here, we can say z is equal to 3 minus 2i plus or minus the square root of 3 minus 2i squared minus 4 times 1 times 1 minus 3i all over 2a, which is 2. Now I guess right now we want to find out 3 minus 2i squared minus 4 outside of 1 minus 3i. And I think we might bring out our new best friend here. I don't want you guys using this at the moment, but I think it's beneficial that you understand that there are tools out there that when we're under the pressure in an exam can help you. So let's have a look at what we can do on our calculator. Now unfortunately your calculator, the new Casio, can't square root a complex number. That's because it can't output an answer that has more than one answer. Each square root will have two answers and the calculator can't output two answers at once. But what we can use it to do is determine this. Am I going to allow you to use this now? No, but I want to show you what you can be doing in the future. In an exam, often you don't have time to worry about things that are, as you get better, this easy. And we can use our calculator to help us. So we get just 1. So we get z equals 3 minus 2i plus or minus 1, the square root of 1 is 1, over 2. We get z equals either 3 plus 1 is 4 minus 2i over 2, or z equals 3 minus 1, which is 2 minus 2i over 2. So 2 minus I, or 1, or 1 plus I. Alright, thanks for watching.